Let us consider the homogeneous system x prime equals a times x, where A is an n by n matrix. We will guess that the solution vector will be of the form of a constant vector, k1, k2 down to kn, times e to the lambda t. And we'll call that constant vector capital lambda. Now, we guessed this form because this was the form when we were studying homogeneous linear differential equations earlier. Well, in order for this to be a solution, we'd have x prime is equal to capital lambda, lambda e to the lambda t. So our homogeneous system now becomes capital lambda, lambda e to lambda t is equal to a lambda e to the lambda t, which can be rewritten as lambda I minus a times capital lambda is equal to the zero vector. So in order to find a non-trivial solution to this equation, we have to find a non-trivial solution to this. Well, that's true, or a non-trivial solution exists when the determinant of lambda I minus a is equal to 0. Well, this is the eigenproblem we studied last time, which means that this lambda, this constant, would be an eigenvector, and then this lambda would be an eigenvalue. There are 3 cases for this here. Just as with the linear differential equations, we can have distinct real roots, we can have repeated real roots, and we can also have complex conjugate roots. And we will study each one in turn. So in the first case we consider distinct real eigenvalues. So this happens when the n by n matrix A has n distinct eigenvalues. Lambda 1, lambda 2 through lambda n. Then we can find a set of n linearly independent eigenvectors. Capital lambda 1, capital lambda 2, up through capital lambda n. Each eigenvector corresponding to an eigenvalue. So we'd say that this eigenvector corresponds to this eigenvalue corresponds to this eigenvalue, so on and so forth. So if we form solution vectors, phi1 equals lambda 1e to lambda 1t, phi2 equals lambda 2 e to the lambda 2t, so on and so forth. These form a fundamental solution set, or a fundamental set of solutions. And then, as we know, the general solution would just be a linear combination of these n solution vectors. So to see this, let's consider the system dx dt is equal to negative 4x plus y plus z. Dy dt is equal to x plus 5y minus z, and then dz dt is equal to y minus 3z. In matrix form, x prime would be equal to the 3 by 3 matrix, negative 4, 1, 1, 1, 5, negative 1, 0, 1, negative 3 times x. So this is our matrix A. So we want to find the eigenvalues of this matrix. So determinant of lambda I minus A is equal to the determinant of the 3 by 3 matrix, lambda plus 4, negative 1, negative 1, negative 1, lambda minus 5, 1, 0, negative 1, lambda plus 3. Taking this determinant, we get lambda plus 3 times lambda squared minus lambda minus 20. So we get the solutions. Lambda is equal to negative 4, or lambda is equal to negative 3, or lambda is equal to 5. So we have our three eigenvalues. Since this is a 3 by 3, we know that we can get three linearly independent eigenvectors, one corresponding to each of the eigenvalues. So if we look at lambda is equal to negative 4, we'll get the matrix 0, minus 1, minus 1, minus 1, minus 9, 1, and then 0, minus 1, minus 1. If we row reduce this, and so this will give us the system that x1 is equal to 10, or let's actually keep it with the variables that we have. So x is equal to 10z, and y is equal to negative z. So you should recall that we can let the z be any value we want. So we'll take our first eigenvector to be the vector 10, negative 1, and 1, which gives us the solution vector 10, negative 1, 1, all times e to the negative 4t. And so we'll keep that in the back of our mind. For the eigenvalue, negative 3, we now get the 3 by 3, 1, negative 1, negative 1, negative 1, negative 8, 1, 0, negative 1, 0. We'll reduce this. This will give us the set x is equal to z and y is equal to 0. So again, z can be anything we want. So we'll take our second eigenvector to be 1, 0, 1, which will give us a second solution vector, 1, 0, 1 times e to the negative 3t. That leaves one more eigenvalue, lambda equals 5. So this will give us 3 by 3, 9, negative 1, negative 1, negative 1, 0, 1, 0, negative 1, and 8, which will row reduce. So we have the system x is equal to z, y is equal to 8z. So we take our third eigenvector to be 1, 8, 1, which gives us our third solution vector, 1, 8, 1, e to the 5t. So our general solution will be C1, 10 minus 1, 1, e to the negative 4t, plus C2 times 1, 0, 1, e to the negative 3t, plus C3 times 1, 8, 1, e to the 5t. We will now go ahead and look at the case where we have a repeated eigenvalue. So that is, we let m be a positive integer such that lambda minus lambda I to the m is a factor of the characteristic polynomial, but lambda minus lambda I to the m plus 1 is not. We would say that lambda I is an eigenvalue of multiplicity m. Now, unlike when we were dealing with just linear equations and roots, we have two cases when we have a repeated eigenvalue. The first case is it is possible to find m linearly independent eigenvectors. That is, the single eigenvalue will give us m linearly independent eigenvectors. In this case, there's no difference between the previous case, so the general solution will look much the same as before. So to see this, let's take a look at the system. X prime is equal to 1, negative 2, 2, negative 2, 1, negative 2, 2, negative 2, and 1, x. So this is our matrix A here. So we want determinant of lambda I minus A. So I have lambda minus 1, 2, negative 2, 2, lambda minus 1, 2, negative 2, 2, and lambda minus 1. This will give us the determinant lambda plus 1 times lambda squared minus 4 lambda minus 5. And this is equal to 0. So we get the solution. Lambda is negative 1 and lambda is 5. Now, lambda equals negative 1 has a multiplicity of 2. So, since I'm studying the first case, this is obviously going to give me 2 linearly independent eigenvectors. So we go lambda equals negative 1. This will give us the 3 by 3, negative 2, 2, negative 2, 2, negative 2, 2, negative 2, 2, negative 2, which will row reduce. So we have the system that x1 is equal to x2 minus x3. So we can form one eigenvector by setting x2 to 1 and x3 to 0. And so we get 1, 1, 0. We can get a second eigenvector by setting x2 to 0 and x3 to 1. And so we get negative 1, 0, 1. So we get 2 linearly independent solution vectors out of this. Phi1, 1, 1, 0, e to the negative t, and then Phi2 is negative 1, 0, 1, e to the negative t. Then we just have to find the eigenvector associated with lambda equals 5. So we have a 3 by 3, 4, 2, negative 2, 2, 4, 2, negative 2, 2, 4. Which reduces and so this will give us the system. X1 is equal to x3 and x2 is equal to negative x3. And so we get our third eigenvector of 1, negative 1, 1, which gives us our third solution vector, 1, negative 1, 1, e to the 5t. And so our general solution, C1 times 1, 1, 0, e to the negative t, plus C2 times negative 1, 0, 1, e to the negative t, plus C3, 1, negative 1, 1, e to the 5t. The second case is that we can only get one eigenvector. From the eigenvalue. In this case, we can form a fundamental set of solutions of the form phi j is equal to the summation from k equals 1 to j of lambda jk t to the j minus k all over j minus k factorial e to the lambda jt. Sorry, that should be a lambda sub I. It's the eigenvalue. Such that 1 is less than or equal to j, less than or equal to m. So j ranges from 1 to the multiplicity. Now this looks like a mess, but I'll show you how to find these using the system x prime equals 2, 1, 6, 0, 2, 5, 0, 0, 2 times x. So we'll go ahead and solve this system now. So once again, this is our coefficient matrix. It's 3 by 3. So we need to do the determinant of lambda I minus a, which is the determinant of lambda minus 2, negative 1, negative 6, 0, lambda minus 2, negative 5, and 0, 0, lambda minus 2. This determinant is lambda minus 2 cubed. That has to be 0. So we get a single eigenvalue, lambda equals 2, and it has a multiplicity of 3. So normally you need to ask yourself throughout the work, can we get 3 linearly independent vectors out of this? If we can, then obviously it would fall into the first case. So lambda equals 2 will give us the 3 by 3 matrix, 0, minus 1, minus 6, 0, 0, minus 5, 0, 0, and 0. So this will give us the system x2 is equal to negative 6x3, and x3 is equal to 0. This, of course, means that x1 can be any real number. Since x3 is 0, x2 is also 0. So we get an eigenvector of 1, 0, 0, which would give us phi1 is equal to 1, 0, 0, e to the 2t. Now, there's no way I can get 2 more eigenvectors out of this system. That would be linearly independent. So I have to find 2 more. And we're going to use that nasty looking thing. Well, we can find a second linearly independent eigenvector by setting up the system lambda 1 is equal to 2i minus a lambda 2, where this 2 is simply the eigenvalue. This is the first eigenvector. This is the second eigenvector that we want. So we just have to solve for lambda 2. All right, so this will give us the system 1, 0, 0 is equal to the 3 by 3 matrix, 0, minus 1, 6, negative 6. 0, 0, negative 5. And 0, 0, 0 times some unknown 3 vector, just call it x, y, z. So if we perform matrix multiplication here, we'll get a 3 vector, negative y minus 6z, negative 5z, and 0. Now remember, this has to equal this 1, 0, 0. So this will give us a system. Negative y minus 6z is equal to 0. Negative 5z is equal to 0. And the last line, 0 equals 0, which is, of course, true. So from here, we know that z is 0. I'm sorry, this is not 0, that's a 1. Which means that y would be negative 1. And x can be any real number. Let's set it equal to 0. So we get our second lambda to be 0, negative 1, 0. So our second solution will be our first vector, so 1, 0, 0, e to the 2t, plus, now, this new eigenvector, 0, minus 1, 0, come back up to the form, times t to the 2 minus 1 over 2 minus 1 factorial, and then that e. So t to the 2 minus 1 is just t. And so this becomes t e to the 2t, because 1 factorial is 1. And so here's our second solution vector. We still need one more. Well, we're going to use the same equation. Lambda 2 is equal to 2I minus a. Lambda 3. Now write this out in its actual matrix form. So we'll get 0 minus 1, 0 is equal to this product up here. I'm not going to reinvent the wheel, so I'm just going to write this vector. Negative y minus 6z, negative 5z, and 0. So this will give us the system. Negative y minus 6z equals 0. Negative 5z is equal to negative 1. And again, 0 equals 0. So z has to be a fifth from that second equation, which means that y would have to be 6/5 from the first equation. And again, x can be any real number. Set it equal to 0 again. So we can take our third eigenvector to be 0, 6/5, 1/5. And so we can take our third solution vector to be the 1, 0, 0, e to the 2t, plus the 0, minus 1, 0, t e to the 2t, now plus this new eigenvector, 0, 6/5, a fifth. Now it's going to be t squared over 2 factorial times e to the 2t. And so this is our third linearly independent solution vector. So our general solution would be C1 times 1, 0, 0, e to the 2t plus C2 e to the 2t times the quantity of 1, 0, 0 plus 0 minus 1, 0 t plus C3 e to the 2t times the quantity 1, 0, 0 plus 0 minus 1, 0 t plus 0, 6/5, 1/5 t squared over 2. And this could be simplified if we wanted, so we could actually write this as C1 1, 0, 0 e to the 2t plus C2 times 1 negative t0 e to the 2t plus C3 times 1 negative t plus 3t squared over 5, and then t squared over 10 e to the 2t. Now, all I did to get this vector was I added these two, and all I did to get this was I added these three. The final case we have to consider is if the eigenvalues are complex. So that is, we have lambda 1 of the form alpha plus beta I, lambda 2 of the form alpha minus beta I, which of course is the complex conjugate of lambda 1. So we represent complex conjugate by putting a horizontal bar over the variable. Both alpha and beta are real numbers. Now, suppose lambda 1 is an eigenvector that corresponds to lambda 1, which is of course alpha plus beta I. Then it would make sense that we'd have two solution vectors. Lambda 1 e to the lambda 1t, and the complex conjugate of lambda 1 e to the complex conjugate of lambda 1t. So we're going to rewrite both of these. So for the first one, we can write it as lambda 1 times e to the alpha t e to the I beta t. And then we can use Euler's formula to write this as lambda 1 e to the alpha t times cosine of beta t plus I sine beta t. The second one, we'll write it as lambda 1 bar, so complex conjugate, e to the alpha t e to the negative I beta t. And again, using Euler's formula, that e to the negative I beta t is cosine of beta t minus I sine of beta t. And these are a fundamental set of solutions. Using superposition, we can then write phi1 is a half times the quantity of lambda 1 plus the complex conjugate of lambda 1 e to the alpha t cosine to the beta t minus I over 2 times negative lambda 1 plus the complex conjugate of lambda 1 e alpha t sine of beta t. And then phi2 would be I over 2 times negative lambda 1 plus complex conjugate of lambda 1 e to the alpha t cosine of beta t plus a half lambda 1 plus complex conjugate of lambda 1 e to the alpha t sine of beta t. Now, it is a known fact from complex analysis that if we take 1/2 z plus z bar and I over 2 negative z plus z bar, where z is a complex number, these both are real numbers. So both of these values will be a real number. It will not be complex, will not have an I. So it makes sense then that these values are real numbers. So to simplify things, we're going to define a vector b1 to be a half lambda 1 plus complex conjugate of lambda 1, and b2 to be I over 2 times negative lambda 1 plus complex conjugate of lambda 1. And both of these will, of course, be reals. They'll be real vectors. So using that, we can form our solution, our two solutions. Phi1 is equal to b1 cosine of beta t minus b2 sine of beta t all times e to the alpha t, and phi2 to be b2 cosine of beta t plus b1 sine of beta t all times e to the alpha t. These form a fundamental solution set. Now, we will also often write this. b1 is defined to be the real component of lambda 1, and b2 is defined to be the imaginary component of lambda 1. Now, to see this in action, let's take a look at the initial value problem given by x prime is equal to 2, 8, negative 1, negative 2 times x, where x of 0 is equal to the vector 2 minus 1. So the first thing we need to do is find the general solution to this equation, and then we'll apply the initial value. So we want the determinant of lambda I minus a. So this will give us the determinant of the 2 by 2 matrix, lambda minus 2, negative 8, 1, and lambda plus 2, which is lambda squared plus 4, and of course that equals 0. So we get lambda 1 is 2i, and the second would be negative 2i. So we're strictly going to work with this 2i one. So we want to find the eigenvector associated with 2i. We'll have a 2 by 2 matrix, negative 2 plus 2i, negative 8, 1, and 2 plus 2i. Row reduce this, 1, 2 plus 2i, 0, 0, which gives us the system. X1 is equal to negative 2 plus 2i x2, and x2 can be any real number. So our eigenvector, let's call it just lambda, is equal to 2 plus 2i, negative 1. I'm picking x2 to be negative 1. Now, I can rewrite this as 2, negative 1, plus 2, 0 times I. This component here is the real part of lambda, and this vector here is the imaginary part of lambda. Remember, the real part is B1, the imaginary part is B2. So using the form above, we can get phi1 is equal to 2, negative 1 cosine of 2t minus 2, 0 sine of 2t. And phi2 is 2, 0 cosine of 2t plus 2, negative 1 sine of 2t. So we can write our general solution in the form of c1 cosine 2t times 2, negative 1. I'm sorry, I royally screwed that one up. We can write it in the form of c1 times 2, negative 1 plus c2 times 2, 0. This whole thing will be times the cosine of 2t, and then plus the quantity of c2, 2, negative 1, minus c1, 2, 0, all times sine of 2t. We now use the initial condition that x of 0 is equal to 2, negative 1. So everywhere we see a t, we're just going to replace it with 0 in here. So this will have to be c1 times 2, negative 1 plus c2 times 2, negative 1. I'm sorry, times c2 times 2, 0. Right, because sine of 0 is 0, so all we're left with is this here. Combine these two together, we'll get 2c1 plus 2c2 and negative c1. So we have the system that 2c1 plus 2c2 has to be 2, whereas negative c1 has to be negative 1, which means, of course, that c1 has to be 1. So if c1 is 1, then the first equation says that c2 is 0. And so our particular solution is phi is equal to 2 negative 1 cosine of 2t minus 2 0 sine of 2t. So that concludes this lesson. I hope you've learned something, and we'll see you in the next one.